Hi everyone, this is Kalyan Kumar this side and welcome back to Chemistry Universe. This is video number part 8 and we are doing still the chemical properties of aldehydes and ketones. We've done a lot of them before. We've done nucleophilic addition, we have done oxidation, we have done reduction, a lot of them. Now it's the turn of very important reactions called name reactions. So I'm going to take one reaction at a time and explain in detail and give some examples as to how these reactions happen. The first one that is in this video, and now we're going to make shorter videos because I'm going to take one reaction at a time. We call this as the aldol condensation. So this is the chemical properties of aldehyde and ketones, and this is video number 8, and this is aldol condensation. So let's get on with the video. All right, so this is video number 8. Aldol condensation. Now let's understand what this does. Now it is seen that when you react two molecules of aldehyde or a molecule of an aldehyde and a ketone, or two molecules of a ketone, all having alpha H, then they seem to react together and to form a dimer kind of a compound. And one of the products that we get is the beta hydroxy aldehyde or beta hydroxy ketone. That's the first product that we get. So this is the way it works. Under the influence of a dilute base or acid, two molecules of an aldehyde or a ketone that have alpha hydrogens may combine to form beta hydroxy aldehyde or beta hydroxy ketone. Now this reaction is called as the Aldol reaction because the product of the reaction of 2 mole of aldehyde is called aldol. Aldol because it contains an aldehyde part, so ald, and an alcohol part, ol. Now the aldol reaction is more favorable for aldehydes than for ketones because of more acidic alpha hydrogen atoms and more electrophilic carbon. Now let me give you an example. Suppose I take acetaldehyde and I take acetone, for example. Now here you will be able to see that this H is more acidic than this H. That is because there is a plus I effect of the CH3. And the second thing is this carbon is more electrophilic than this carbon for the same reason as the plus I effect of CH3. And in this reaction, you need the H to be acidic and you need the carbon to be electrophilic. So aldol reactions are basically called aldol, otherwise you could have called it ketol also. But generally we'll refer to as aldehydes, aldol, because most of the reactions of aldol are seen with aldehydes rather than ketones. So you have 2 molecules of aldehyde in the presence of a base, and look at what happens. You get a beta, this is the alpha carbon, this is the beta carbon, you get a beta hydroxy aldehyde. Okay. Now, of course, we'll talk about the mechanism in a short while. Now, heating this, if I heat this in the presence of an acid and base, what happens is this OH gets lost along with one of the H here as H2O, and there is a double bond formed here. So, this particular reaction is called aldol reaction. But when you combine this reaction with the elimination of water, that is forming the double bond here, which will be a separate reaction in itself, you will need to add an acid or base and then heat. That combined reaction, that means this reaction and that reaction together, would be called aldol condensation reaction. So heating the aldol product in either acid or base leads to dehydration because the double bond generated is in conjugation with a carbonyl group, which would definitely make it more stable, because remember, this double bond would be conjugated with the double bond O here. And So if I take this aldol and add a weak acid like NaHSO3, you can add any weak acid, you can add acetic acid also. And then when you heat it, you're going to get this product, alpha beta unsaturated aldehyde. And these two reactions combined are called aldol condensation. Now remember, this can be catalyzed in both base and acid. So let's first check out the base catalyzed condensation. So base catalyzed mechanism. So what happens first is you have the aldehyde, and remember we clearly said that have alpha hydrogens. The reason we need alpha hydrogens is because this is going to act as an acid. This is going to give this acidic H to the base. So the base comes and picks up this H and you get a carbanion. Now this carbanion is resonance stabilized with a C double bond O. Now this carbanion then meets another molecule of aldehyde, and the carbon attacks a carbonyl carbon of the aldehyde. This pi bond goes up and you get something like this. And then, since the solvent is water, water is able to give H plus to this, because ultimately it will lead to the formation of alcohols, and water, remember, is actually more acidic than alcohols. Methanol is the only alcohol that is more acidic than water. Otherwise, all alcohols are less acidic than water, meaning water can easily give the proton to O minus. So now this way you are able to get beta hydroxyaldehyde. If you want to understand this mechanism in detail further, you just make sure that you pause the video, go through each step, ask yourself, are you able to understand each step, and only don't go forward with the video. Now what happens is, now this is, okay, this first reaction has an RDS, it is the RDS if the OH minus concentration is low. That means the more acidic H is preferred here. But the second step would be the RDS if the OH minus is high in amount. That means carbanions are produced rapidly. So it is the attack of the carbanions on the carbonyl carbon that decides the rate of the reaction. Now, then what happens is, once you get the beta hydroxyaldehyde, now if you react it with OH minus, now remember this OH is a bad leaving group. We know that. And we've already done elimination, if you remember, in alkyl halides. So when you have a bad leaving group, and that too you have a withdrawing group attached to this carbon, I mean, if this is the OH that is going, let's assume this is alpha carbon and this is beta carbon. I mean, you can say alpha beta with respect to either aldehyde or alcohol. Right now I'm doing it with respect to alcohol. So the beta carbon has a withdrawing group. Then the mechanism that is preferred for elimination is even Cb. So what will happen is, using even Cb, first H plus will be lost to form a carbanion, which is stabilized by the CHO. And then this will attack and the bad leaving group will leave, and you will get, on heating, the alpha beta unsaturated aldehyde, which is called crotonaldehyde. Now, this can be also done in acid. In acid, it's pretty simple. It will be simply E2, because OH will get protonated. It becomes a good leaving group. Now you have a simple E2 mechanism happening, and you get the same crotonaldehyde. Okay. Now let's do acid catalyzed aldol. Again, you have this aldehyde. You must have added some kind of an acid. Let's say the HX is the acid. Now the O lone pair picks up the H plus, and you get this protonate. Now the X minus takes the proton from the alpha carbon, and you get this double bond, and this bond moves to OH. You get an enol basically. This is enolization. Now in enols, you'll always find this carbon is highly nucleophilic, because this lone pair has a tendency to resonate with this pi bond, and it will always make this carbon into a carbanion. So when it meets, so this is the enol. So when it meets another aldehyde, the pi bond goes here. This pi bond goes to carbon. Carbon is a nucleophile. The other aldehyde, carbonyl carbon, will act as an electrophile, and this will go here, this will go up, and you will find this happening. Okay. And then, of course, you have this intramolecular proton exchange and you get the beta hydroxyaldehyde. And then, of course, you can convert that into the protonaldehyde or the alpha beta unsaturated aldehyde using acid and base. Now, generally, what we do is we keep the concentration of OH minus low because then it tends to behave more as a base rather than as a nucleophile. So, I'm going to give you one particular reaction which is pretty interesting of aldol condensation, and I want you to pause at every step and make the product on your own. So first ask yourself, I take acetone and I do OH minus and I do heat. If I give both OH minus and heat, that means you're required to produce aldol condensation product. If I only give OH minus, make the aldol reaction product, the first one, beta hydroxy aldehyde or ketone. So pause the video now and make the product on your own. Now, here is the answer. So basically what happens is, this will lose a carbon, a proton, okay? And then it will meet another aldehyde, another ketone, because you only have acetone here. This will attack here. This will go up. So what is the aldol you will get? You will get CH2, C, OH, and 2 CH3s here, right? That's what you'll get. And then when you remove this OH and this H, you'll get CH3, CO, CH double bond, C, and this is 2 CH3s. All right. So the product you'll get would be this. I've just flipped it across. Just see. I've just flipped it and made this. So this is the product of the first reaction. Now I want you to do this again. I again add OH minus and again add acetone. Now you would wonder, where do I take the alpha H and where do I make this thing attack? Remember, the beta H is also highly acidic because this one has more resonating structures. It has this and then it has this also. So the beta hydrogen of the alpha beta unsaturated ketone, this particular H is going to be more acidic. So this will lose the H and it will attack that ketone. What will happen? You will get this as minus. It will attack this. Again, you'll get an OH and again, you'll get a double bond. So if you try to make the product, it's going to look like something like this. Okay. So this you should try on your own. Again, try this. Again, make one more acetone with OH minus and now remove this H. Make the product. Pause the video, make the product. So here is the answer. You will get something like this. Okay. Now, as you can see, this is, now one may wonder, is this, will this keep on going? Well, what do you think will happen if I do OH minus now? Now, I'm not adding acetone again. Meaning, now you're going to get an intramolecular thing. Because remember, this itself has a carbonyl compound, carbon, and this itself has an alpha H. Now, you might again wonder, even this had that, even this had that. Well, let me first show you the reaction, then you'll yourself understand what happens. This will lose the H, okay? This will lose the H. All right. Now, this will attack this. Pi bond shifts. What do you think will happen after I add water? Won't you get this? Just check for yourself. It's going to be a 6-membered ring. Now, can you understand why it only happened in this case? Because only in this case, you'll get a stable 6-membered ring. In the others, you will not get a stable ring. So now, what do you think will happen to this if I heat it? So if I heat it, don't you think this OH and this H will go? And won't you get a benzene ring? In fact, you get this. Right? Now, as you can understand, aldol condensation is possible between two aldehydes, which could be same or different. can happen between two ketones, which could be same or different, or it could happen with one aldehyde and one ketone. Now, if both carbonyl compounds are same, then it is called a simple or a self-aldol. And when the two compounds are different, it is called a mixed or a cross-aldol. So self-aldol is the one when you are given only one aldehyde or one ketone and given OH minus. Now, they may not write two molecules, remember. They may not write the coefficient of the aldehyde or the ketone as 2 because it is understood. I mean, obviously, you're not going to take one molecule. You're going to take a sample, right? So what will happen is that when you are given an aldehyde or a ketone and simply given OH minus, it implies, obviously, it is going to react with its own another molecule, okay? But if there are two different ones, they will give you two different aldehydes, ketones, or a mix of the two. So in self-aldol, only one product is formed. So that's pretty fine. In cross-aldol, you have 4 products formed. Now, can you guess why those 4 products are formed? Well, if I take, let's say I take 2 aldehydes, it doesn't matter whether I take 2 aldehydes or an aldehyde or a ketone or 2 different ketones. So I take A and B. Now, A can do a self-aldol, one product. B can do a self-aldol, one product. And A and B can do a mixed aldol. But in that too, A can lose the proton and attack the carbonyl carbon of B, or B can lose the proton and attack the carbonyl carbon of A. And since A and B are different, these 2 products will be different. So you will get 4 products in this case. In cross-aldol, if 2 aldehydes are reacting, then the major product is that in which the carbonyl is formed from the aldehyde, which has more acidic H, and the carbonyl carbon that is more electrophilic gets attacked by the carbonyl. So this is the way it goes. If you have 2 aldehydes, now you might wonder, okay, which one will form the carbonyl and which one will get attacked? Well, that will form the carbonyl which has more acidic H, and that carbon will be attacked, that carbonyl carbon will be attacked which has more electrophilic nature. And that will be evident when I give you some examples. Okay? So in cross-aldol, if one aldehyde reacts with a ketone, then the major product is that in which the carbonyl is formed from the ketone, and the aldehyde is the one that gets attacked by the carbonyl. Now what you need to understand is if I take a ketone and an aldehyde, assuming both have alpha H, the major product is the one where the alpha is lost by the ketone, even though that H is less acidic. Because here the RDS, when aldehyde and ketones react or 2 aldehydes react, generally we keep the OH minus concentration always a little high so that the attack of the carbonyl on the carbonyl carbon becomes the key step or the RDS. So what happens is that if you have 2 aldehydes, different aldehydes, or in this case an aldehyde or a ketone, invariably the carbonyl will form from the ketone and it will attack the aldehyde. That will always be the major product. So use this to make the products that I give you. Alright. Now to make the aldol reaction product without doing much of the mechanism, first of all decide which one will lose the alpha H and whose carbonyl carbon is attacked. Okay. So first decide which will lose the alpha H and whose carbonyl carbon will get attacked. Then what you do, secondly, write the compound whose carbonyl carbon is attacked, and below it write the compound whose alpha H will be lost, such that the alpha carbon from which the H will be lost is just below the carbonyl compound. For example, take this. Now I'm taking 2 molecules of acetaldehyde, so it's not going to be much of a problem. So here I'll show you. So first I take 1 molecule of aldehyde and I write that one whose carbonyl carbon will get attacked. Now obviously this carbonyl carbon is going to get attacked. This is why I'm writing first. Now I'll write the alpha H of that aldehyde whose alpha H will be lost and form a carbonyl. Now since both of them are the same aldehyde, it doesn't matter. But if they were different aldehydes, it would matter. So first of all, decide whose carbonyl carbon is attacked, which will lose the carbon ion, which will form the carbon ion, and write that alpha carbon just below this. Okay. Now what you have to do is do the following. Make this pi bond go to O, make this O get this H, and let this bond come between the two atoms. Won't you get this? Just check. Pi bond goes to O, O captures the H, the CH bond goes between the two carbon atoms. Won't you get this? So this is how you make the aldol reaction product without having to resort to the mechanism. On the other hand, if you want to make the aldol condensation product, do the following. Write the O of the aldehyde or ketone whose carbonyl carbon will be attacked on the right side. So what I'll do is I'll write C double bond O, I'll write H, and I'll write CH3. This is the carbonyl carbon that will be attacked. Now write the alpha carbon along with its two hydrogens. And of course, it's going to be a CH3, but write the third H separately. And then write it like this. Now all you have to do is lose water like this. And join the two carbons by the double bond. Here I'll show you. This is the O. And this is the 2H facing the O. And remove this water. And join the two carbons by a double bond. So obviously I must have added OH minus first. Then resorted to heat it. And remember, even if I don't write the acid, I simply write heat, it will still dehydrate. You'll get this. Okay, so that way you can easily do it. So using this, you have to write the major product of the aldol condensation in each of the following cases. So first, check this out. I have acetaldehyde and I have propanaldehyde. And I do all the necessary reagents. Now pause the video now. Decide, and I want the aldol condensation product, okay? So decide whose carbonyl carbon will be attacked. Decide whose alpha H is going to be lost. And then make the product. So obviously, the carbonyl carbon attack is more important. So this is the one which will attack. This is the carbon that will be attacked. So you should write its double bond O like this. And this is the alpha carbon of the other aldehyde. Write its 2H facing the O. Remember, it has also a CH3, and write CHO. Now remove water. What do you think you'll get? So won't you get this? Yeah, just check. Try one more. Look at this. Make the product of aldol condensation. Now here it's pretty simple because the second one, the benzaldehyde, does not even have the alpha H. So you will get this. Because the benzaldehyde is the one whose carbonyl carbon will be attacked. And this particular reaction with benzaldehyde and acetaldehyde, it's called the Claisen-Schmidt condensation. It's a form of aldol condensation. Now, I want you to try this, even though we've already made it before, but pause the video, don't look back, just do the formation of the product. So here is the answer. It should be this. So if you have any issue with any of these, make sure you write them in the comments below that you have an issue with this particular reaction, and we can sort it out. So now try acetaldehyde and acetone. Now remember, I already told you with an aldehyde and a ketone, it is the ketone that will lose alpha H, and aldehyde is the one whose carbonyl carbon will be attacked. So what do you think will be the product? Pause. Make the product. So here is the answer. It will be this. So you need to check for yourself. Try it with this. This is called acetophenone. And since it's a self, it's simple. Alpha H of 1 will be lost. O CO, or the O of one CO will be lost, you will get this. And I want you to try this. Pause the video. So alpha H is lost. It'll attack. Right? So I'm going to show you here how to write this. Well, you can write it like this. Keep this O on the right. And in the other one, write it like this. And remember, this guy has 2H. So this H2O goes. And this carbon will be doubly bonded with this carbon. You should get something like this. Let's look at some more examples. Try this. Now this is a sequence. First I do reductive ozonolysis of this. I get A. Then I do OH minus and the same. I get B. Write A and B. Pause the video. Make sure to play the video only after you make the product on your own. Now, obviously, when you do the ozonolysis of this, it's pretty simple. This double bond will break and you'll get double bond O on both carbons. So here it doesn't matter because both are, it's a very symmetrical one. So let's say this loses the carbon ion, this forms a carbon ion and this attacks this carbonyl carbon. So basically this O will go and the 2H from here will go. You will get B as this. You'll form a 5-membered ring. Just check this out on your own. You'll be able to do it. Now this is intramolecular aldol condensation, which we also see in the case of acetone. Intramolecular aldol condensation. Now remember, whenever there is a possibility of an intramolecular and an intermolecular, intramolecular will be favored. It will be favored because, and that too of course, if it is going to form a 5 or a 6-membered ring. That is because intramolecular distances are shorter than intermolecular distances. So make sure to understand this, that intramolecular is favored over inter if you can get a stable 5 or a 6-membered ring, which is why in this case it is happening. So an intramolecular reaction is readily favored if the reaction leads to the formation of 5 or a 6-membered ring. Now, if one is an aldehyde and other is a ketone, it's the ketone which forms the carbon ion, which we've already discussed, and this carbon ion will attack the carbonyl carbon of the aldehyde in such a manner that 5 or 6-membered ring is formed. So try this. Pause the video now. Make sure you do the product on your own. So obviously the first A is going to be this reductive ozonolysis. Now remember, ketone should form the carbon ion. The ketone will lose the 2H. It can either lose this, which means it will attack here. If it attacks here, you will get a 1, a 2, a 3, a 4, a 5 and a 6-membered ring. If it were to lose this alpha H and this were to attack here, it will form a 1, a 2, a 3, a 4-membered ring, which is not advisable. So this will lose the 2H and this will lose the O. You will get this one. Check on our own. And with that, we come to the end of aldol condensation. So as you saw, this was a pretty short video, and but focusing on only one reaction at a time. And in the later part of other lessons also, I'll try to take up smaller reactions. Generally, I used to have this principle that, I need to complete all the properties in one go. But then there are a lot of people who commented that, we would prefer to have small segments of maybe even a single or maybe 2 reactions together, so that it becomes easy for us to, go through that and watch it and note it down. So I said, fine. So aldol condensation, I've done it separately, and I'll do all the other things also separately. The next one coming up would be video number 9. That is going to focus on Cannizzaro reaction. They're all related in a way. So anyway, so aldol condensation is done. And make sure to watch this video as many times as you need to watch. And I hope this video did help you in understanding aldol condensation. And if you have any questions, anything, any comments, you can put them in the comment section below. With that, this is Kalyan Kumar signing off. Have a wonderful day, a productive day, and make sure that you don't waste your time. Make sure that when you watch these videos, you make notes. And thank you for watching this.